Graphs of trigonometric functions. So, for the graphing of trigonometric functions, it's really good to go and look at some graphing software and really play around with these so you can get a handle on what's happening. So we're going to begin by looking at y equals sine x, and we'll consider that in detail first before going on to other the cosine and tangent. So if we consider a circle, and we think of some point P, and its radius is 1, and if we think this is a right angle, and we've got this moving in this direction, so this point P is kind of moving around it like a Ferris wheel. If you think of a Ferris wheel going round and round and round, this is like a Ferris wheel going round and round and round. And if we were to map the point P as it moves round this circle with the positive horizontal axis, with x as the positive horizontal axis, and as the angle coming around here, we would get a sine graph. So we start, a little bit longer. So we'd go from 1 to -1. It starts at 0, so say that was the start there, and it would make a nice sine graph with a maximum at 90, this bit here would be 180, minimum at 270 and 360. So this is this y equals sine x, where for 0 degrees less than or equal to x less than or equal to 360 degrees. So the displacement of P moves from 0 to 1 to -1 and back to 0 from this position here, from this x axis. If we could imagine it starting here and then it going up to get to 1, and it goes back to 0, then down to -1, and then back to 0 as the angle here changes. And this x on this axis is the angle that we're going round. We can do the same for the cosine. Now this time the cosine starts at 1, up here, it doesn't start at 0, it starts at 1. And it also goes through the same period of 360 degrees. And this time it goes through the 0 at 90, its minimum is 180, comes back through 0 at 270, and is a maximum at 360. You can continue both of these graphs, and the periods of them will continue. They'll just they will repeat in the same way in the x positive and in the x negative direction, because both sine and cosine functions are periodic. They keep repeating themselves. The period is defined as the length of one repetition. Or cycle. For both sine and cosine functions, the period is 360 degrees or 2 pi. The amplitude is defined as the distance between the maximum or minimum point and the principal axis. So for the cosine and sine functions, the amplitude is 1. Because of the symmetry in the sine function, we can show some important relationships. I'll write these down here, and it's important to go and look at these, but also then to look at them and look at them also for the cosine function. And that's a good wee exercise to go and do. Play with the graphing software and see what the relationships are. So if you have sine of minus x, that's the same as minus sine x. The sine of 180 minus x equals sine x. Sine of 180 plus x equals minus sine x. The sine of 360 minus x equals minus sine x. And the sine of 360 plus x equals sine x. Now, I'm just going to put these here, but take these away, go and graph them, look at them, how they work, and it just will give you that real depth of understanding. It's something to get a real handle of it you need to go and do yourself, and the same sorts of results will come out of the cosine, and it's all because of the period on the cyclic action of the trigonometric functions. Now, that was sine and cosine, and you can see they were really similar. In fact, you can think of the sine and cosine as just a shift of the other one. The tangent, on the other hand, is completely different. It's such a different type of function. It's really quite bizarre. So, you've got x and you've got y. And this tangent goes like this. And then you have these points in the tangent curve which are called asymptotes, where the well, this is 0, I'll put these numbers in, this is 90, this is minus 90. So as x approaches 90, the tangent goes up, and really increases, but it never reaches the asymptote. But it reappears down here just after 90, it comes down here. And then you've got the same, oops. It's a bit, oh, it's a terrible one. Oh, I can't draw it nicely at all. Still not very nice. That's 180, and it does the same at 270, and then and that's 360. And if we continue along here, that's 450. And this is one here. So this is, and then that one, we've got another one coming up here. So this is our tangent. It repeats, it's got a period, this time of 180 or pi radians. The dashed lines at plus or minus 90, 270 and 450 degrees are asymptotes. And as we say, the tangent never reaches them. And interestingly, the tangent has no amplitude, but it has this kind of turning point here. And again, just like with the sine and cosine rule, because of the fact that it repeats, there is symmetry, and you can play with, if you were to map the tan of minus x, the tan of 180 minus x, all these different identities that we looked at with the sine rule, if you map them and see what happens to the tangent, it's an interesting exercise and gives you a real understanding of how the function operates. Now, trigonometric functions can be transformed in the same way that any other function can be transformed. And it's really important, if you go back, if you've forgotten how different transformations like translations, stretches, inversions, all these different things, have a look back at how they work and what the rules are, because trigonometric functions are obeyed by the same types of rules. So we're going to look at transformations for y equals a f of x, y equals f of a of x, y equals f of x plus a, and y equals f of x plus a. And we're going to look at these different transformations, and then we're also going to look at how to combine them. So let's think of the graph of y equals a sine x. And I want to be able to change colour. So firstly, I'm going to do I'll just get this black for now. So we've got our normal y equals sine x, where this is 1 and this is minus 1. Now, I'm going to do 2 . So this is now y equals 2 sine x. So the maximum is at 2 and the minimum is at minus 2. So it has a stretch factor of 2 parallel to the y-axis, and the amplitude is 2, and the period is 360 degrees. So the period, when you put the stretch on it, the period doesn't change, but the amplitude does. It gets stretched. And the stretch factor is the value of A. We're going to look at y equals sine AX. So likewise, I'm going to draw y equals sine of x. And now I'm going to draw y equals sine 2x. So this time, I'm actually going to put some numbers in first because it will help. This is 90, this is 180, 270 and 360. So now we have so for this one, we have a stretch factor of a half. This time it's parallel to the x-axis, if you remember what we did before with transformations. And but the amplitude is 1, it remains the same. But the period is now 180. So if you see, when we've y equals 2x, the period has halved because the stretch factor is a half parallel to the x-axis. So one period is half of what it was previously. So we've got 2 cycles with our y equals sine 2x for our one cycle of the y equals sine x. Now let's look at y equals a plus sine x. So again, we're going to draw our normal sine, and that's 1, and that's minus 1. Should have made that bigger for a minute. It's a bit smaller. And put them in. So 1 and minus 1. Now we are this is y equals sine x. I'll better put some numbers in just to help us. This is 270 and that's obviously 180 and that's 360. So now we're going to do, we want to draw y equals 1 plus sine x. So unsurprisingly, this is 0, so this is now going to go up to 1. And so we just have a mirror of what we had before. So we have a translation (0, 1). So with the trigonomic transformations, the same rules for vectors as our other transformations apply. So this is a translation of 1, 0, so it affects the y coordinate. And the amplitude is 1 and the period is 360. Let's now look at y equals sine x plus a. Oh, it's not very good. Ah! Tests my drawing. That's still pretty terrible. Never mind. So x, so this is our still our 90. This is still our 270. Now we're going to look at y equals sine x plus 90. So what this does is it moves everything back. So this is like taking our sine graph and dragging it along to here. So this is a translation of minus 90, 0. So remember for vector that's x plus 90, but the translation is in the x coordinate goes to minus 90. Again, the period is still 360 and our amplitude is 1. Now, interestingly, if you look at this, our turquoise curve, the turquoise curve is actually a cosine. So, what we've discovered here, y equals sine x plus 90 is the same as cosine of x. So let's do a few examples. So on a grid we're going to sketch y equals sine x, y equals sine x minus 90 for 0 less than or equal to x less than or equal to 360. So when you're asked to do these sketching questions, pay close attention to the range. So for our y equals x, we just do a nice little, it's not a nice little sine graph. And we'll put some numbers in, 90, 180, 270 and 360. So it's important you put your some values on your on the axes, 1, minus 1. And so y, so that's y equals sine x. To make it easy, I'm just going to put, to differentiate it, I'm going to put this in a different colour. So y equals sine x minus 90 is a translation of y equals sine x by the vector So it's on the x, dealing with the x coordinate, so and that's minus, so that's going to be plus. It's 90, 0. So this time, our curve gets moved in this direction. So this is going to be our positive. This is going to be 0. So it's going to come like that. And this is our y equals sine x minus 90. Now we can combine transformations. So say we were wanting to sketch the function y equals 2 cosine x plus 90 plus 1. From 0 less than or equal to x less than or equal to 360. What we would be doing is we're going to build up the transformation in steps. So we're going to have lots of draw lots of wee sketches here so we can just keep track of it. So we'll do our cosine graph. 1, minus 1, 90, 180, 270, 360. Okay? And we'll keep track of what's changing. So we know this is, the period is 360 and the amplitude, I'm just going to call it amp, equals 1. And this is cosine of x. Now we're going to add in the next step. So this time we're going to do cosine of x plus 90. So that is a translation of the cosine of x by vector minus 90, 0. So it's like taking this graph and moving it (90°) to the left. So what was it, 90, which is 0, will now be 0. And it's going to go down and along. So we've still got minus 1 and 1. This is now 90. So what was it, 180 now goes to 90. What was it, 270 now goes to 180. And 270 is now a maximum. And then, let's go down to, dear me. And that'll be 360. So the period is still 360 and the amplitude is still 1. So what's the next step we're going to put into our we're going to take this graph and we're going to do y equals 2 cosine x plus 90. So this is a stretch factor. Oops, that's a stretch. Of 2 parallel to the y-axis. So the period is 360. And find out the amplitude is. So this is going to be, so now, bigger. There we go. So now we're going to have 2 and minus 2. So this is still going down here, but this time it's going to go, we're still going to have 90, 180, 270 and 360. But this time it's going to go like this. So the amplitude will equal 2. Now I'm not going to have room to do another axis, so I'm actually just going to draw it on the same axis as this, but I'm going to change the colour so it doesn't get confusing. So now we want to do y equals 2 cosine x plus 90 plus 1. So this is going to translate 2 cosine x plus 90, what we've just done, this, by vector 0, 1. So this will move everything up 1. So we're going to, this will be coming down here. This will be up to 3. This is the black back on. This is minus 1, and this will be 1. So the period remains the same. It's still 360, and the amplitude is still 2. Okay, we're going to do a couple more examples. So if we've got f of x is 3 cosine 2x for 0 less than or equal to x less than or equal to 360, what are the period and amplitude? Find the maximum and minimum points, sketch the graph, and then sketch 1 plus 3 cosine 2x on the same graph. Okay, so if we look here, we've got a 2. So this is our, let me put my black back on. So for the period, we take our 360, which would be our period for a cosine, and we divide it by 2 because we've got that stretch factor there, parallel to the x-axis, and that's going to give us 180. The amplitude we've got 3 times the cosine, so it's going to be 3. So the maximum and minimum So let's think about, I'm just going to draw a wee sketch of a normal cosine. That's 0, there's 90, 180, 270 and 360. So our period is going to be half of this. So we're still going to have at for the normal cosine x, I'm going to write them down what we have. We have 0, 1. We have 180 minus 1. And we have 361. And if we continued that, we'd have 540 minus 1 and 721. So that's for the cosine. But for our function f of x, the period is halved. So we'll still have one at 0, and the amplitude is now 3. But the maximum will be at 3. The next one, half of that is going to be 90. And the amplitude is minus 3. And for this one, half of 360 is 180. And that's going to be positive 3. Then it will be 270 minus 3 and 360 plus 3. So we can use this information now to draw our graph. We do 3 minus 3, and we've got 90, 180, 270 and 360. So we'll have, whoops a daisy. Ah, like that. And next one we want to do sketch y equals 1 plus 3 cosine 2x. So we take this and we're going to move it up 1. And it'll just be a mirror. And that'll be minus 2, and that'll be 4. And we'll do one last example. Change that to black. So On the same grid, map y equals sine 2x and y equals 1 plus 3 cosine 2x for 0 less than or equal to x less than or equal to 360. And state the number of solutions of the equation two sine x equals 1 plus 3 cosine 2x. So, oopsie daisy. For this one, you would have graph paper and you would have to be quite semi-accurate with what you're doing. So let's think about our sine 2x. So it's going to be a sine graph, but it's stretched to half. So you're going to have 90, 180, 270 and 360. So instead that's going to be positive here. Oh dear. So it's 1 minus 1. Now, our 1 plus cosine 3 cosine 2x is just what we've just been drawing. So it goes up to 4, comes down to minus 2, and I'm going to change the colour. So these are crossing here, 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 and here. So there's 1, 2, 3, 4. There's going to be 4 solutions to the equation. So I hope that helps.